Assalamualaikum. We are from Group 7, Computer, Architecture and Organization, Section 1. We will present our group project. My name is Muhammad Naim Shazim bin Azam with matric number CE210155. I will present our introduction of this project. This project aims to study by looking at a clear picture of the concept of the instruction set in the computer and the process it works when receiving and carrying on our assignment. Cache is a small memory or just the data that is located between processor and the main memory. Actually, it is from main memory too, but it is already used before and not moved to the main memory again for a few times or as long we do not delete or move it manually, or it is replaced with other which is newly used data. We will make an overview about the instruction set by using Paracache. Paracache is a simulator to show how computer work in virtual from during some tasks. We can adjust the value of memory size, cache size and offset byte. It has two options of instruction which is load and store. While doing the experiment, the simulator will show the movement of the computer architecture and organization to execute the instruction. Execution in computer and software engineer mean the process by which computer or virtual machine read and operate based on the instruction content in the program.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf bin Muhammad Safi'i. My matric number AE200100. So for my part, I will explain the methodology. So caches are divided into blocks which may be of various sizes. The number of blocks in a cache is usually a power of 2. A direct mapped cache is the simplest approach where each main memory address maps to exactly one cache block. So the figure here is the example of 8 block cache, which one block holding 1 byte. So this figure shows an example of a 16-byte main memory and a 4-byte cache. For memory address 0, 4, 8 and 12 all map to cache block 0, while memory address 1, 5, 9 and 13 is mapped to cache 1 and so on. The mod approach may be used to discover which cache block will contain memory address if we wanted to read it from memory. However, other addresses might possibly map to the same cache block. To distinguish between several memory addresses that map to the same cache block, we need to add tags to the cache which provide the remaining address bits. So basically the index is at the right side and the tag is at the left side. So for example, for 0110, the tag is 01 at the left and the index is 10 at the right side. So at the start, the cache is initially empty and does not contain any valid data. All of the valid bits are set to 0 when the system is initially set, and when data is loaded into a particular cache block, the corresponding valid bit is set to 1. So to make it clearer, we will simulate the cache mapping using Paracache. So for our group, we will do 2 simulation, direct mapped cache and 2-way set associative cache. So the specifications for our group is cache size 16, memory size 256, offset bits 2, and load instructions is 3, 4, 5, 1D, 11, 25, A, 13 and 27. So I will pass to the next presenter, Muhammad Raihan. He will demonstrate the direct mapped cache. Thank you.
Okay, my name is Muhammad Raihan bin Muhammad Noazmi. My matric number AE200105. Okay, so for my part, I will explain about direct map cache. So we are using Paracache virtual simulator. Okay, to get started, we need to first specify the cache configuration first. Okay, so for our project, we will be using cache size is 16, memory size of 256 and offset bit is 2. Then we submit. Okay, so as we can see here in the instruction breakdown, the tag is 4 bit, index is 2 bit, offset is 2 bit. So this is the offset bit 2 here, and the index is 2 bit. How do we get 2 bit? Is 16 divided by 4 from the cache size. 16 divided 4. Why we divided by 4? Because in the memory block we get we have 4 bit. Okay, so to know the tag is instruction length minus index minus offset, so we will get 4 bit. Okay, so next we insert the 10 instruction. For our group, we will be using this instruction 3, 4, 5, 1D, 11, 25, 8, 13 and 27. Okay, first for instruction 3 we submit. Okay, now as we can see here, the instruction that we have submit has been converted from hex to binary into this instruction breakdown. Okay, as we can see here, the 0000 is tag, 00 is index, 11 is offset. Okay, next. Okay, index requested here is 00, so we refer to index 0. As we know, 0 is 00, 1 is 01, 2 is 10, 3 is 11. So index here show that we need to refer 00, so index 0, and then we click next, and we will be checking the data invalid, no data, and also in the tag no data. So we will obtain a cache miss. Okay, after cache miss, cache table will update accordingly. Okay, so next. Okay, one cycle has been completed. Okay, for next cycle we need to submit the load instruction first. Okay, so now we have new in instruction breakdown 000, 00 and 11. Okay, this time we refer in the index 0 because in tag in instruction breakdown is 00, so index in cache table we refer at index 0, and we will be analyze in the valid. We have there is a value 1, and in the tag cache table is as the same as in instruction breakdown, so we will be obtain cache hit. Okay, so next. Okay, for next load instruction is 4. We submit it first. Okay, now for instruction 4, instruction now has been converted from hex to binary, so the 4 have insert in instruction breakdown. So now the tag is 000, the index will be 01, and offset is 00. Okay, so in instruction breakdown it says that we need to refer in cache table 01, so 01 means 1. So in index 1, we will analyze the data in the valid and the tag at both, since there are no data, so we will be obtain a cache miss. After that, the cache table will be updated. Okay, so next is for the next instruction 5. We submit first. Okay, now it has been converted in this instruction breakdown. Okay, so now the tag is 0000, index 01, offset is 01. So we refer to cache table as in instruction breakdown is 01, so we need to refer in 1 because 1 is 01. So we click next to check the data in valid and tag. As we can see here, the data in tag and in the instruction breakdown is the same, so the result obtained will be catch hit. Okay, that's the for the complete one cycle. So the remaining 11, 25, A, 13 and 27 also the same as we can see here. If we submit 1D, we will just fast forward it to obtain the result. So this is for 11, we just fast forward it. Okay, 25 and then A, 13 and lastly 27. Okay, so we have complete the cycle of 10 instruction. Okay, so as we can see here, the statistic of our instruction, so we can obtain that our hit rate is 40% and miss rate is 60%, and this is the list of previous instruction. Where did we miss and where did the instruction hit? Okay, that's all.
So next we will move to two-way set associative cache. So replacement policies we use is FIFO, and write policies write back, write on allocate, cache size 16, memory size 256, offset bits 2. So we click submit, and this is the instruction breakdown, and this is the initial cache table. It doesn't contain any valid data yet. So this is our first instruction, and this is our next load instruction, and then we submit. The tree will be converted into binary, so the index is 0. The searching will go into cache table index 0 here, so we will check the valid. Since the table doesn't contain any data, the valid is set to 0. Therefore, the both of AND gate is missed and OR gate is missed. So the table will updated with new data with the tag 0. Then we move to the next instruction, which is 3. So we search in index 0 and the valid here is 1, and then we compare the tag. So because of the tag is the same, then the first gate AND gate is hit, while the second one is missed. So the OR gate is hit because one of the AND gate is hit. Therefore we can get the cache hit, and then the table will update it with the data again. We move to the next instruction, which is 4. Then this is the conversion into binary. The index is 1, so the searching will go into the index 1. So we check the valid value, and because of both of the valid is 0, the AND gate is missed and also OR gate is missed. So the table will update it. And next we move to the next instruction, which is 5. So the index is 1, and then we will search in index 1. So the valid is 1 here and valid is 0. So we add the valid one, we compare the tag value. So because of this 0 and this is 0, we can get the cache hit, and also at the OR gate we will get hit because one of the AND gate is hit. Then the table will update it with new data again, and then we move to the next instruction, which is 1D. So we submit, and the index is 1, so the searching will go into index 1. So the valid here is 1, and then we compare with the tag. So at here the tag is 00011, while here is 0. Therefore we will get the miss, and because of the AND gate is missed, the OR gate is also missed. And then the table will be updated. The table here will be updated with new tag, which is 3. And then we will move to the next instruction, which is 11. Index 0, so it will go to 0. Valid 1. And then we compare the tag. The tag is not same, So is missed, and OR gate is also missed. Then the table here will be updated with the new tag, which is 2. Then move to the next instruction, which is 25, and the index is 1, so we will go to 1, and both of the valid is 1, but we need to check the tag. So here the tag is 00100, while here is 0 and 3. So it is not the same. Both of AND gate is missed, and also OR gate is missed. So the table here will be updated with the new tag 4. So this instruction is same, so I will just fast forward. It is missed, because of the instruction is in index 0, so the data in the table in the index 0 will be updated with the new data. So this is the next instruction, which is 13 bit 0, so index 0, it will search in index 0. Both of the valid value is 1, so we compare the tag. So here is 00010, the tag here is 1 and this is 2, so 00010 is 2, therefore the second cache table will hit when we compare the tag. So one of the AND gate is hit, we will get the cache hit. So the same step occur in the last instruction, and that's one. Compare the tag, and the first table is hit, therefore we will get the cache hit. So it will be updated with the new data. So that's all for the instruction, and this is the statistics for our list of previous instructions. And the hit rate we get is 40%, and miss rate is 60%. So for discussion, direct mapped cache is a cache organization where each memory block can be mapped to only one specific cache block. The memory address and the hash function decide the mapping. This implies that every memory block may be kept at a set spot in the cache. The cache determines if the related cache block is legitimate and whether the tag value matches when the processor demands data. If so, the data is retrieved because there has been a cache hit. If not, it is considered a cache miss, and the information is retrieved from the main memory. Two-way set associative cache allows each memory block to be mapped to two cache blocks within a set. Each set in the cache has a specific amount of cache blocks. The cache is divided into sets. Similar to direct mapped cache, the mapping is decided by the memory address and hash function. The cache determines if any of the cache blocks in the relevant set are legitimate when the processor requests data, as well as whether the tag value matches. If so, the data is retrieved because there has been a cache hit. If not, there is a cache miss, and the next cache block in the set is chosen using a replacement strategy like FIFO, first in, first out. So this is some of the difference between direct mapping and set associative mapping. So first, for direct mapping, it's only one comparison because of using direct formulas to get the effective cache address. For set associative mapping, it needs comparisons equal to the number of blocks per set, as the set can contain more than one block. There is one possible location in the cache organization for each block from main memory because we have a fixed formula. So the mapping of the main memory block can be done with a particular cache block of any direct mapped cache. It has least number of tag bits, while set associative mapping it has less tag bits than associative mapping and more tag bits than direct mapping. And lastly, for direct mapping, search time is less here because there is one possible location in the cache organization for each block from main memory, while for set associative mapping, search time increases with number of blocks per set.
Okay, next we move on to recommendation part. Okay, so for direct map cache, we can implement cache bypassing techniques by identify frequently accessed memory blocks, or maybe hot data, and bypass them directly to the processor. This is to avoid cache access altogether. This reduces cache contention and improve overall performance. Next, we can also explore cache compression by using compression algorithm to store more data in a smaller cache space. This can effectively increase cache capacity and reduce cache miss. Lastly, to employ victim caching. Instead of evicting a cache line to main memory, we store it in a victim cache. This helps reduce cache miss by retrieving recently evicted cache lines directly from the victim cache instead of accessing main memory. So for the next part is for two-way set associative cache. Okay, first we can consider higher associativity levels by increasing the number of cache line per set to reduce conflict and improve cache hit rates. Higher associativity levels such as 4-way or maybe 8-way can further enhance cache performance. Next, we can dynamic the reordering of memory access by analyzing the memory access pattern and dynamically reorder the sequence of memory access to minimize conflict in the cache. Okay, this technique helps to maximize cache utilization and reduce the miss ratio. Last but not least is to adaptive replacement policies. By implementing replacement policies that adapt dynamically to workload characteristics, these policies consider factors such as access frequency, recency and spatial locality to make informed decisions about which cache line to evict. So this will improve the cache hit rates.
Okay, I will present our conclusion of this group project. After doing a simulation, we can see a clear visualization of the data execution in the computer using Parakit simulator. We can conclude that cache play an important role in computer architecture to give high performance and fast data execution for user. The concept of cache and execution process is also already become more clear. During the process, we can see the data taken from the true cache to bring into the process. The data has been taken is cache hit, while wrong data is cache miss. We can conclude the direct method cache associate as memory block with a specific cache block, but two-way set associative cache can map two cache block in one set. It can make faster access for the data and avoid more cache miss because all set can store more than one data at one time. This increases the performance of the computer execution. So a two-way set executive is better than direct method. So that's all from our group. Thank you.